Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the linear momentum equations and its applications. So, we have seen the linear momentum equations and the various kinds of applications like say when a jet striking on a plate, how it is how the momentum equation can be utilized for the purpose of calculating various parameters and the force applied, etc. So, now in this lecture we will be discussing say the moment of momentum equation. So, what we have seen the linear momentum, so say the direct momentum is considered, but many fluid mechanics problem we will be discussing say the moment of momentum, that means the angular momentum. So, in the moment of momentum generally what will be coming is which it involves torques and angular momentum. So, torque means the moment of a force with respect to an axis or a point. So, when we consider the moment of a force with respect to a fluid media or a control, say a control volume where we consider the force. So, the torque means the torque of that fluid mass is it is the moment of the force with respect to an axis or a particular point. So, and then say in the moment of momentum what we are considering is say what kind of torques are developing with respect to the fluid system, and then what is how the angular momentum develops. So, that is what we are going to discuss in today's lecture. So, here now to develop this moment of momentum equations we will be again using Newton's second law of motion to a particular the particle of a fluid. So, let us consider a control volume which we considered earlier. So, now if we consider say the total derivative d by dt of v rho del v, where del v is the corresponding volume, that should be equal to the effective force on that particle. So, with respect to Newton's second law we can write the rate of change of momentum, that means d by dt of rho v del v, that should be equal to the net force on that particle. So, that gives in this equation number 1. So, now where v is the particle velocity, delta f is the particle the resultant external force acting on that particle. So, now we will form moment of each side with respect to the origin, so that with respect to the initial the coordinate system. So, now if you consider with respect to the earlier equation d by dt v rho del v is equal to del f particle, the force on that particle. So, now if we form moment of each side with respect to the original inertial coordinate system, we can write r cross d by dt v rho del v, that is equal to r cross del f particles, that means the force on the particles. So, as in equation number 2, where r is the position vector which we consider. So, now say with respect to what we are discussing here is, so you can see here if you consider say a fluid control volume like this, and then if you consider particular particles. So, if you consider say the position vector from which we are considering, so this is r, and then we are taking the angular momentum or the moment of say first we are considering we have the rho v into del v, that gives the momentum, and then we are considering rate of say the change of momentum, that gives the rate of change of momentum. So, that we are equating to the say r cross d by dt v rho del v is equal to r cross del of particles, where r is the position vector as shown in this figure. So, now say this equation number 2 we can write with respect to the earlier equation. So, here this equation number 2 we can write like this: d by dt the total derivative d by dt r cross v rho del v, where rho is the mass density, v is the velocity of the particle, r is the position vector. So, that should be equal to r cross del of particle, where del f is the force acting on that particular particle. So, now this is as far as a particle which we considered here in a system. So if this is the system which we are considering, so this is the system which we are considering for this derivation of the equation. So now this is the particular particle we are considering. So we have now considered this particular particle, and then what is the its torque or its momentum what we are considering. So now let us consider the total system. So for the total system is concerned, what we can do is we can integrate for the system, integral for the system d by dt r cross v rho del v, that should be equal to integral r cross f for the system. So now we are considering the total system. Earlier we considered for a particular particle what are the forces acting. Now for the total system we can integrate with respect to this the left hand side of equation number 3, and then we can sum up all the forces throughout the particle, so that sigma r cross f for the system. So this is the momentum equation for a system. So now we can see that the time rate of change from the earlier equation what is written here in equation number 4, we can see the time rate of change of momentum of system is equal to sum of the external torques acting on the system. So what gives this equation number 4 is say you can see it gives the time rate of change of moment of the system that we are equating to the sum of the external torques acting on the system. So now for a control volume, instantaneously coincident with the system, we can see that the torques acting on the system and control volume contents will be identical. So the control volume which we consider here, so that will be the control volume for the particular system which we are considering. The torques acting on the system will be identical with the control volume contents what we are considering in the earlier system of the equation. So now earlier we have seen the Reynolds transport theorem. So we have already discussed the applications of Reynolds transport theorem. Many problems Reynolds transport theorem is used to derive the basic equation. So now if we use the Reynolds transport equation to derive the final equation for the moment equation, so using the Reynolds transport theorem we can write with respect to the previous equation number 4. So now if you use the Reynolds transport theorem, we can write del by del t for the control volume r cross v rho del v. So this indicates the volume plus integral or the control surface r cross v rho v dot n dA, that is equal to sigma r cross f for the control volume. So here now in the earlier equation number 4 we have used the Reynolds transport theorem to derive say for the system. So as we can see here, if you consider the control volume, what happens in the control volume inside, and then on the surfaces what happens. So that is what is we are doing. So on the surfaces, control surfaces what happens, and then what happens to control volume. So that is the basic principle we have utilized in most of the earlier derivations with respect to the Reynolds transport theorem. So now finally we get this equation number 5. So now this is say this equation number 5 is applicable for unsteady state flow. So now if we consider a steady state flow system, we can write this we can express this equation as for a rotating system at steady state. We can write the torque exerted on the fluid by a rotating element is equal to angular momentum of fluid leaving out of the control volume minus angular momentum of fluid entering the control volume. So finally say the same thing what we have seen in this equation number 5, which is applicable for the unsteady flow conditions. But if we consider the steady flow condition, we can say that for the rotating system. So as we have seen here, the momentum equation we are deriving for a system where angular velocity or angular momentum, or the rotational system like a turbine or a pumps or say that kind of system, or a sprinkler, lawn sprinkler, this kinds of system we are using this momentum equation. So if we consider for a rotating system at steady state condition, we can write finally that the torque exerted on the fluid by rotating element is equal to the angular moment of fluid leaving out of the control volume minus the angular moment of fluid entering the control volume. So finally this T, the torque can be written as in this equation here, T is equal to rho Q into sigma sigma V into R out minus sigma V R in. So, where rho is the mass density, T is the torque, rho is the mass density, Q is the discharge, V is the velocity, absolute velocity, and R is the say the position vector, or the where the system is concerned, that we are considering R as the position vector. So, that this gives the final equation for the with respect to moment of equation for the steady state flow condition. So, the same thing for unsteady state, the general equation is given in equation number 5. So, now this momentum equations have got large number of applications in fluid mechanics or in engineering problems. Say wherever angular velocity of angular momentum is very important. So, if you consider, say for example, the motion of turbines, and then what happens to the fluid flow taking place with respect to the turbine, or say while considering a flow in a pump. So, how the system is working, or say many other kinds of system where the angular momentum or the angular velocity is coming to picture. So, there this momentum equations have got large number of applications. So, this we can apply for the machines that rotate or tend to rotate around a single axis, just like in turbo machines, or say as we have discussed, turbines, pumps, propellers, fans, all these places, lawn sprinklers, mower blades, etc. all these places we can utilize this moment of momentum principle or momentum equations either at steady state or unsteady state. So, we will be discussing few of the applications now with respect to the moment of momentum equations. So, first one what we are going to consider is application with respect to a lawn sprinkler. So, we will consider a simple system here, which is which is a so called lawn sprinkler. So, all of you know how a lawn sprinkler works. So, you can see that say the water will be coming through a small pipe, and then there will be a rotating arm like this, and then there will be two jets at the end. Say if the water is coming through a pipe like this, and then you can see that there will be two jets at the end, and then it will be rotating like this. So, this is so called the lawn sprinkler. So, here you can see in this figure say how we are just going to derive the system equation with respect to the lawn sprinkler in particular. So, you can see the fluid, the water or the fluid is coming in this direction, the flow is coming in this direction, and there is a rotating arm here. So, and at the both ends of the rotating arms there is a small say nozzles through which the water will be coming out. So, now we can consider a control volume like this. So, once the water flows through the system, the sprinkler system, you can see that say the water will be going this direction and the other direction through the two nozzles, and then the system will be rotating. So, this is so called a lawn sprinkler. So, now if you consider the figure here, so you can see this U2 is the velocity, the absolute velocity of the water flowing through the nozzle or coming through the jet action here, and similarly on this side also, if you consider symmetric case, this will be U2, here also it will be U2, and then say the rotation of the arm, if it is omega, and R is the from the center line, R is the distance to the where the rotating arm angle. So, where R is shown here, and then if you consider the velocity triangle, the polar vector say diagram with respect to this say the movement of the fluid, or with respect to movement of the rotating arm, we can see that if this angle is alpha, and here this total angle is beta, and say V2 is the say the U2 is the velocity of jet relative to the tangential velocity. So, we can draw the velocity triangle like this, and now with respect to this we will further explain how we can say find out the various parameters like say the torque or the say one parameter is given, how to determine the other parameter. So let us, for this particular system which we consider here, so let Q be the discharge coming throughout through the pipe. So that Q is divided into two nozzles. So if A is the area of two outlets, so relative velocity at exit will be Q by 2A. So here flow is, water is coming through the pipe here, which is discharge is Q, and that is divided into two nozzles, nozzle say A and B, and then it is going through the two outlets. So if A is the area of the two outlets, so relative velocity at exit will be Q by 2A. So that is equal to U2, and with respect to this figure, this beta is the angle of jet with the direction of rotation, and V2 is the velocity of arm, which we can be put as R into omega, where R is this distance and omega is the rotation speed of the arm. So V2 is equal to R into omega, where omega is the angular velocity and U2 is the absolute velocity, as we have seen, and then its tangential component. So here you can see that if this is say U2, then its tangential component you can just draw U2. So so tangential component V2 is equal to U2 cos alpha, and from the velocity triangle drawn here, this is the velocity triangle, we can draw U2 bar minus V2 bar is equal to U2 bar, that is the relative velocity. So now with respect to the velocity triangle, we can write V2 plus U2 cos beta is equal to UV2, that is equal to U2 cos alpha. So now with respect to the system here, we can find out the force exerted. So we will find out the force exerted by fluid on the system. So that can be written as F is equal to minus rho q u v2, where u v2 is the relative velocity. So F is equal to minus rho q u v2, that is equal to minus rho q into v2 plus u2 cos beta. So where q is the discharge, rho is the mass density. Now we can write the retarding torque due to the bearing friction, etc. We can write T is equal to rho q r into v2 plus u2 cos beta, where v2 is equal to omega r2, that is equal to omega r. So now if you want to find out for this system, if you want to find out what is the angular velocity of the rotation, so omega we can write as omega is equal to minus u2 cos beta by r, that minus T by rho q r square, whereas T is the torque which we have already derived. So omega is equal to, we can get the omega is equal to minus u2 cos beta by r minus T by rho q r square. So now this is the omega, the angular velocity of the system. So now if you want to find out the maximum speed of sprinkler, say when torque is equal to 0, we can write omega max is equal to minus u2 cos beta by r. Also we can write uv2 is equal to u2 cos alpha is equal to 0, where alpha is the angle of inclination of absolute velocity with respect to tangential direction, which is equal to 90 degree here. And now with respect to the earlier figure, say when this beta, this angle beta is equal to, or this angle beta is equal to 180 degree, we can write T is equal to minus rho q r into omega r minus u2, and now when T is equal to 0, we will be getting omega is equal to v2 by r. So now if you want to find out the torque required to hold the sprinkler in fixed position or to prevent from rotation, we can write that T is when omega is equal to 0. So we can write T0, that is the torque required to hold the sprinkler in fixed position. T0 is equal to rho q r u2 cos beta. So like this for this system which we have seen here, say which is a lawn sprinkler, which is a simple system, we can find out the torque, or if you want to find out the angular velocity of the rotating arm, we can find out the various parameter using the moment of momentum or angular momentum principle, or the moment of momentum equation. We can find out the various parameters. So this is one of the simplest application of this moment of momentum equation, say as in the case of a lawn sprinkler. So now, other than this, there are, as we have already discussed, there are large number of applications. We will be also discussing some of the applications like what happens in a turbine or in a pump. So here we can see that say the simple principle where the steady state flow condition is prevailing, we are assuming steady state flow condition, and then how the moment of momentum equation is applied. So you can see, say this figure is taken from Fluid Mechanics, Streeter, Wiley and Bedford McGrail publications, Boston. So you can see how say the application momentum principle in a turbine case. You can see that the turbine is concerned, you can see when the water is coming and heating on the vanes of the turbine, it starts to rotate, and then that is transferred the power, so due to the rotation effect in a magnetic field, we get the power. So that is what is happening in a turbine. And in the other application is in the case of a pump, we can use pump to to extract water from a well. So you can see that there the pump is the if the turbine is used, we are using to generate power, but in the case of pumps we are using power to rotate the pump, and then we are rising either water or any other fluid which we are considering. So this moment of momentum principle can be utilized to say derive various relationship, either in the case of a turbine or pumps, or in the case of various turbo machines. So now let us consider the case of a turbine as discussed as shown in this figure. So in the case of a turbine, it is as we have seen in the earlier figure, these are all rotating mechanisms. So in the case of a turbine, let us see how this moment of momentum principle can be utilized. So here say the turbines, actually you can see that the turbine extract the useful work from fluid energy. So as I mentioned, in the case of turbine, say the large velocity, say jet velocity is hitting on the blades of the turbine, and then it is rotating in a magnetic field, and then we are extracting the power. So that means the case of turbines, it extracts useful work from the fluid energy. So that is what we are doing in the case of turbine. So let us consider the steady flow through a control volume with a circular symmetry. So this is the where the various blades are say mounted on an axle like this in the case of a turbine. So this figure is also taken from Streeter et al. 1998 Fluid Mechanics book. So various say blades are located like this, and now we are considering the control volume boundaries like this. So this is one boundary, this is the second boundary, and then say the from the center line of the axle, this R1 is the distance to the internal boundary, R2 is the distance to the external boundary. And if you consider a particular blade, say where the fluid is heating, either water jet or any other kind of fluid is heating, so here alpha 1 is this angle, and V1 is this velocity with respect to this say the blade, and VR1 is the radial velocity, and say you can see that we can have tangential component and also the radial component, and say with respect to this figure, so how to derive the various say how to apply this moment of momentum equations that we will be discussing here. So before going for the how to utilize this moment of momentum principle or equation, so now we use certain assumptions here in the case of a turbine or a pump. So, the assumptions used here are the friction force is neglected. The friction force with respect to what is happening here is neglected, and the relative velocity of fluid is always tangent to the vane. So, you can see the the various vanes attached to or mounted with respect to this axle. So, its relative velocity of fluid is always tangent to the vane. And then the third assumption is circular symmetry is there, and then it permits the use of moment of moment equation in the simple form, just as the steady state form which we have seen. So, these are some of the assumptions, essential assumptions used in the derivation or the application of this moment or momentum principle. So, now to derive the relationship, so let us consider the torque on fluid within the control volume. So, we are now considering the control volume here. You can see the control volume with respect to the boundary and the blades attached. So, with respect to this control volume, the torque of fluid within the control volume T is equal to rho q r into Vt out minus r into Vt in, where Vt is the tangential velocity with respect to out and with respect to in. So, this is the Vt out here, and then Vt in is considered here. So, this is Vt, the tangential velocity in, and this is tangential velocity out. So, the torque on the fluid with, say, now you can see that when the turbine is rotating, the fluid is this entire boundary, the control volume will be filled with fluid, and then it is rotating. So, now the torque on the fluid within the control volume which we consider is T is equal to, if rho is the mass density, Q is the discharge, and R is this say either R1 or R2, or this R is the radius to the external or internal boundary which we consider. So, T is equal to, torque is equal to rho Q R into Vt out minus r into Vt in. So, where Vt is the tangential velocity, where here this rho q r into Vt out, that gives the moment of momentum leaving from the system, and rho q into r into Vt in, that gives the moment of momentum entering the system which we consider. So, here as you can see, this is a control volume which you are considering. So, there will be momentum entering and momentum leaving, and that gives the difference is taken, and then we are finding out the torque on fluid within the control volume. So, rho q r into Vt out, so that gives the moment of momentum leaving, and rho q r into Vt in gives the moment of momentum entering the control volume which we consider. So, now as in the previous case of the sprinkler system, here also we will consider the polar vector diagram. So, if you consider the polar vector diagram, so for the entrance is concerned. So, here as in this figure, if you consider the entrance, that means with respect to this system here. So, for this the polar vector diagram can be drawn here. So, where V is the absolute fluid velocity, U is the peripheral velocity of the runner. So, this is the runner which we consider. So, now this B1 is the velocity in this direction, and beta 1 is this angle, and U is the U1 corresponds to, for the with respect to the subscript 1 indicates the entrance, and subscript 2 indicates the exit. So, V is the absolute fluid velocity, U is the peripheral velocity of runner, and V small v is the fluid velocity relative to the runner. So, this V1 is the absolute say fluid velocity which we consider for the entrance is concerned, and then U1 is the with respect to the peripheral velocity of the runner which we consider here, and then say V R1 that is the radial velocity which with respect to the system which we consider, and then say for exit conditions are concerned, this gives V2 which is related to absolute fluid velocity with respect to the exit, and then say and the U2 is with respect to the peripheral velocity of the runner, and beta 2 is corresponding angle. So, and VU gives the absolute velocity, the component of the absolute velocity in tangential direction, and VR gives the absolute velocity component normal to the periphery. So, we can see that here the tangential component and then the radial component is considered. So, VR gives the absolute velocity component normal to the periphery. So, finally, with respect to this system which we consider here, we can write T is equal to rho q R2 V2 cos alpha 2, and this alpha 2 is drawn here, minus R1 V1 cos alpha 1. That gives the torque for the system, that is equal to rho q R2 VU2 with respect to the system we consider VU2 or defined, minus R1 VU1. So, where this if you define m dash as the mass per unit time flowing, that is equal to rho q, so we can write rho q out will be equal to rho q in, since the control volume is concerned, whatever the flow going in will be that will be coming out from the system. So, finally, the torque which we are considering here, torque on the fluid within the control volume, we can write T is equal to rho q into R2 V2 cos alpha minus R1 V1 cos alpha 1, that is equal to rho q into R2 VU2 minus R1 VU1. So, finally, this can be written as m dash, which is the mass per unit time flowing, into R2 VU2 minus R1 VU1. So, now say we have actually the principle what we are discussed here is applicable for the case of a turbine or a pump or a propeller, whatever which we consider. So, in the case of a turbine, we can see that the torque will be negative, the moment of momentum decreases. So, as I mentioned, the fluid with a high velocity is entering to the turbine, and then say that is trying to rotate the turbine. So, in the case of a turbine, you can see that the as far as the fluid is concerned, the moment of momentum decreases, so that the torque will be negative. But in the case of a pump, what we consider, the case of a pump, we can see that we are giving electric or the power to the pump, and then pump is giving instead of the turbine extract the power from the fluid, but in the case of pump, what the pump doing is, it is imparting power to the momentum to the fluid which it is pumping. So, for a pump, T will be positive, so fluid momentum increases through the control volume. In the case of a turbine, you can see that momentum decreases. So, this is the essential difference between a turbine and a pump. The moment of momentum decreases for a turbine, the moment of momentum increases for a pump through the control volume which we consider. And if T is equal to 0, as in passages where there are no vanes, we can write we can see that this R VU will be constant. So, we can see that a free vortex motion which is the tangential component of the velocity varying inversely with respect to radius is formed. So, this is so called a free vortex motion where T is equal to 0, as in the case of passages or where no vanes. So, now from the discussion we can see that pumps, blowers, compressors etc. add energy to the fluid by means of runners with vanes attached to a shaft, but in the case of turbine, it is extracting energy from the fluid moving. So, this way we can utilize the moment of momentum equation or the moment of momentum principle which we discussed here with respect to the angular velocity, angular momentum, what we have discussed, we can utilize in the case of turbo machines, turbines, pumps, then blowers, compressors, propellers etc. we can utilize. So, initially we have seen a simple system just like in a sprinkler system, and then we have seen the case of a pump or a turbine where the moment of momentum principle can be utilized. So, here we can see that we have considered a steady state situation only with various assumptions which we have discussed. So, before closing this section, we will be discussing one more numerical examples. So, we have seen various applications of the moment of momentum principles or the equation moment of momentum equation. So, how we can we have also seen the applications in the case of sprinkler system rotating sprinkler system, or in the case of a pump or turbine. So, now we will see a numerical examples to further understand how we are utilizing this moment of momentum equation or moment of momentum principle. So, the numerical example which we are considering here is again as a sprinkler system, a rotating say arm with respect to two nozzles. So, here the problem is as shown in figure, a lawn sprinkler is used for irrigation. So, the diameter of nozzle is 10 millimeter at the end of the rotating arms. The nozzle discharges water with a velocity of 12 meter per second. We have to find out the torque required to hold rotating arm stationary, and then constant speed of rotation of the arm if free to rotate. So, this is the problem. So, here you can see a sprinkler system. Say the arm length is from the from the axis or where the water supplied, from that it is 25 centimeter to the left and 35 centimeter to the right, and there are two nozzles, one nozzle at A and another at B, and from the nozzle the velocity is already given as 12 meter per second on this side, and other side also 12 meter per second in the opposite directions as shown in this figure, and then the nozzle diameter is given as 10 millimeter at the end of the rotating arm, and the velocity is 12 meter per second. So, we have to calculate the torque required to hold the rotating system stationary, and then we have to find out the constant speed of rotation of the arm. So, now we will solve this problem by using the moment of momentum equational principle which we derived in the case of a sprinkler system or in the general system which we have seen. So, now here the diameter of nozzle is given as 10 millimeter and the velocity is given as 12 meter per second. So, area of each nozzle we can calculate pi by 4 into 0.01 square. So, that will give the value of the area of each nozzle as 0.40785 meter square, and then we can find out the discharge through the nozzle. Since the velocity is given, area of section is known. So, we will get discharge through the nozzle A into V. So, that gives 0.000942 meter cube per second. So, now the first part of the problem, this simple problem, is to find out the torque to hold rotating arm stationary. So, torque by water through the nozzle A, we can write rho Q into V A into R A, where rho is the mass density, Q is the discharge coming through the system, V A is the velocity at A, and R A is the distance from the axis to the nozzle at A. So, this we can write as rho Q into V A into R A. So, rho is say we can write like this. So, here rho is 9810 by 9.81, and Q is also found into, so that multiplied by the velocity V A 12 into the distance. So, here you can see the distance is 0.25 meter from this location. So, from here to here. So, that is gives we get the torque by water through the nozzle as 2.826 Newton meter. So, that gives the torque. So, now torque by water through the nozzle B. So, for the second nozzle, here the second nozzle is here at this location. So, that gives, we can write the same equation, rho Q V B into R B. So, R B is 35 centimeter here, and then that gives rho is 9810 by 9.81 into Q is 0.000942 into VB is again 12 into 0.35. So, 3.956 Newton meter, and finally, we can find the total torque to hold the rotating arm stationary. That will be equal to torque exerted by water on the sprinkler. So, we can add both cases, 2.826 plus 3.956, that will give 6.782 Newton meter. So, now that is the torque required to hold the rotating arm stationary. So, that is the first part of the problem. Second part of this simple problem is we have to find out the constant speed of rotation of the arm. So, if omega is the angular speed of rotation of the sprinkler, we can write absolute velocity of flow of water at nozzles at A and B can be written as V1 is equal to 12 minus this 0.25 is the distance here. So, V1 is equal to 12 minus 0.25 into omega, where this 0.25 is the distance from the say axis to the nozzle A, 0.25 omega, and similarly V2 at this location will be 12 minus 0.35 omega, since 35 centimeter is this distance. So, now the torque exerted by water coming out at A on sprinkler, we can write rho q V1 RA. So, that is 9810 by 9.81 into the discharge. So, this this V1 we will substitute here. So, 12 minus 0.25 omega into 0.25. So, that will give 0.2355 into 12 minus 0.25 omega. And then the torque exerted by water coming out at B on sprinkler, so rho q V2 into RB, we can find out say 9810 by 981 into the discharge Q into 12 minus 0.35 omega into 0.35. So, that is equal to 0.3297 into 12 minus 0.35 omega. So, now say the total torque exerted by water we can find out by adding what happens at location A and at location B. So, we can add total torque exerted by water. So, that is equal to 0.2355 into 12 minus 0.25 omega plus 0.3297 into 12 minus 0.35 omega. So, now the question is, we want to find out the constant speed of rotation of arm if free to rotate. So, we can see that resultant torque should be equal to 0 for this condition. So, we can equate this to 0. So, from which we can find out omega, the angular velocity of the rotating arm. So, we finally, if we solve the problem, we get omega as 38.92 radians per second. If you want to find out the RPM, revolutions per minute, we can find out omega is equal to pi n by 60. So, that is equal to 38.92. So, that is n, we can find out n is equal to 38.92 into 60 by 2 pi. So, from which we can find out it will be approximately 372 revolutions per minute. So, that gives the angular velocity and the speed of rotation. So, like this, this is a simple problem of the case which we considered is a sprinkler system with a rotating arm. So, we were trying to find out the torque exerted, and then we were trying to find out say the speed of rotation of the arm. So, in a similar way we can utilize the momentum equation in an effective way to solve a number of problems. Either it can be the sprinkler system which we consider, which is one of the simple most problem, or the same way we can solve the problems like in the case of a turbine or in the pumps where we can approximate into steady state conditions, or even in the case of unsteady flow also we can consider by using this general equation as given in this equation number 5, where we can consider the general equation. So, this is wherever unsteady state condition is also considered. So, these are some of the important say how we are getting the momentum equation, and where we can apply various cases we have seen. So, now the last few lectures we were discussing on the dynamics of fluid motion. So, now we will summarize what we have seen in this particular chapter on the dynamics of fluid motion. So, to summarize, so we have seen the various problems, various cases, various how the system with respect to dynamics of fluid motion in this particular chapter. So, here what we tried to do is to understand the fluid motion with the concerned force. So, the kinematics of fluid motion we have seen, we have not considered the force which is acting upon this control volume, but in this dynamics of fluid motion we have considered the with respect to the force we are trying to understand the fluid motion equation, and then as we have seen at the beginning, we have discussed about the Euler equation, how to derive the Euler equation and what are the applications of Euler equations, and then also we have seen the Bernoulli's theorem. We have derived the Bernoulli's theorem, and which is say with respect to ideal flow condition, but in many practical cases we can utilize the Bernoulli's equations, and then further we can extend to the general energy equations. So that also we have seen as in the various problems we have seen here. So say in this dynamics of fluid flow, which we have seen in this particular chapter, say various applications. So say we have introduced the problem with respect to various systems, and then the Euler's equation, Bernoulli's equation and its applications we have seen, and then we discussed what is happening with respect to say we have derived the linear momentum equations, and then say for the linear momentum equations how the various applications we have discussed, and then finally we have seen the with respect to wherever the case where the angular momentum or the moment of momentum principle is applied. So like in the case of various say wherever say in the case of turbine, turbo machines or pumps, or say the simple system of a sprinkler. So we have seen the last case in the say the moment of moment equation and its application. So these are some of the important system, say in the as to summarize what we have done in the dynamics of fluid motion. So now what we have seen is say after say this dynamics of fluid motion, we will be discussing various say the fluid mechanics say systems say like a laminar flow, turbine flow in detail, and then we will be deriving various fundamentals equation just say for the various systems, and then further we will be going the advanced, we will be discussing the advanced topics on the fluid mechanics. So the next chapter we will be discussing is laminar flow and turbine flow, say its theory, and then say in the application, say as far as pipe flow is concerned, laminar flow in pipes, say turbine flow in pipes, we will be discussing in the next section.